Good evening, everyone. My name is Evgeni Matveev. I'm the Education Outreach Coordinator for the Elk River Alliance, but today I'll be speaking to you on behalf of the Elk River Watershed Collaborative Monitoring Program, which is the collaborative that put this event together. I just want to say thank you, everybody, to coming out. This is so awesome to see so many community members out who care about their water come to events like this. And yeah, as George said, I'll be speaking more on what stories we can tell with data. There's so much data being collected on the water, but how can we turn all this data into a big picture overview of our watershed? So the collaborative was started about 3 years ago with the goal of uniting a lot of different knowledge holders and interest groups under one umbrella to feel the pulse of the river from all kinds of different perspectives, including indigenous knowledge, local knowledge, and scientific knowledge. So currently there are 9 partners, including the Canadian Wildlife Federation, Elk River Guiding, BC Ministry of Environment and Climate Change Strategy, Yakutak-Nakluit, TEC, Living Lakes Canada, North Cole, City of Fernie, and the Elk River Alliance. Over the last couple of years, the collaborative has narrowed down 3 different themes that will be the focus of the monitoring program. And that is climate change-driven flooding and drought, fish habitat, and Tanaha land and water uses. In the last 2 months, the Elk River Alliance and Yakutak-Nakluit partnered together to put in an application for funding for a wide-scale land use study of Yakutak-Nakluit's past and current land and water uses. But for today, I'm going to focus primarily on the 2 scientific themes, so the first 2 here. The collaborative uses the adaptive monitoring framework to guide its program design, and this allows for continuous engagement with communities, such as what we're doing right now. It also allows for continuous reevaluation of the methodology so that we can ensure that our monitoring work continues to be efficient, effective, and answering the right questions that we need to be answered. So over the last 3 years, we've engaged with communities during events such as this. Some of you may have been to my presentation a year and a half ago on Elk Valley land and water. We framed the questions, so the 3 themes that I've just outlined. And now it's time to design the monitoring program. But one of the really important things when it comes to designing a monitoring program is knowing what we already know so that we can know what we don't know. We need to collect all of the available data and see what it's telling us. So to learn from existing data, we need to access all of these different databases that we've heard about in all of the talks today and put them into one single database. Then we need to visualize that data to see if we can see any emergent trends. And only after that can we test some of the hypotheses that we have about our water quality. And then after that, we can assess what we don't know and what we can't answer with the data that we currently have so that we can direct our monitoring efforts in the most efficient way towards answering the questions that we really need answered. So we've taken data from the 5 public data repositories, including the Columbia Basin Water Hub, the Environmental Monitoring System and the BC Data Catalog, the Canadian Aquatic Biomonitoring Network, and the Water Survey of Canada. Some of these you've heard about already tonight. And we've taken all of this data and we've put it into a single database, and it was massive. It was absolutely unwieldy. It was way too big to do anything with, and so it had to be filtered down. So we so far are focusing on data within the Elk River watershed, only from streams and rivers, so not lakes or groundwater, and only on selected metrics that we know to be biologically important. After all of that filtering, we were still left with 369 sites and 59 parameters. So it's still an absolutely massive database. On this map, you see all of the sites that we've extracted. Each point represents a separate site. And what you can see here is that a lot of them are pink, and a lot of them are focused up here. That makes sense because these are TEC monitoring sites. So TEC does a ton of monitoring, by far the most monitoring in the valley, and a lot of it is compliance monitoring for the mines. But something else that you may notice, there's actually a lot of organizations that have data on our valley and on our water. An important thing to point out is that some of these organizations may have just one site or maybe monitoring just one parameter, but they've been monitoring it for years and years. Or maybe they just have one site, but they monitor a lot of parameters. So each one of these organizations that monitors the water is really important because they provide their own perspective on the water quality. So after that, it's time to visualize the data to see if we can see any emerging trends. In the next few slides, I'll be showing you a bunch of graphs. And I just want to go through them here so that I won't go over them over and over again. On the y-axis, we always have the parameter in units. So the parameter can be something like temperature or flow or pH or whatever. And on the x-axis, we have, that's going to vary. So to visualize long-term variation, we're going to have time in years. So it's going to be the entire record just splayed out. To visualize seasonal variation, we're going to take all of those years and superimpose them onto each other to essentially have 1 year to see if we can see any patterns within the season. And then we're going to visualize spatial variation by having each discrete site on the x-axis. And then basically this will allow us to compare different sites to see if there's any trends in spatial variation. So let's start with something that is well known to a lot of us. This is a graph showing flow of the Elk River just at the Fernie monitoring site, monitored by the Water Survey of Canada. This record goes all the way back to the 1970s and all the way to current day. And something that you might notice immediately is we have these regular little spikes. And you might think, oh, this is probably seasonal variation, and you'd be right. If we take all of this data and overlap it over each other within a single year, we see a very clear seasonal trend. So you can see here that this period of May to June, you have the highest flows. And we know this intuitively, because when we look at the river during this time, the water levels are high and the water is murky. And what we also know, and we don't really need a graph, but why not, is that the snowpack that's been accumulating since October starts to suddenly melt really quickly in this May, June, July period. So all of the snowpack melts into the watershed, increasing the water levels. We can also visualize the murkiness of the water by looking at the turbidity here. And you can see that, in fact, yeah, during this May, June period, you have the highest levels of turbidity. We can visualize individual years to look at events that some of you may be familiar with. Here you can see this spike is the 1995 flood. This spike over here is the 2013 flood, which some of you may remember. And this little blip over here was just a few years ago, the atmospheric river event that wiped out Coal Creek. So something that I really want to impress here is that data is not numbers or dots on a graph, and it's not like, it's not this abstraction. It is related to real-world events that we experience on a day-to-day basis. We can visualize the data spatially to also be able to tell something that we intuitively know. This graph is arranged from the most upstream site all the way close to the Elk Lakes to the most downstream site all the way at the outflow to Lake Koocanusa. And you can see that as you go through these sites, you increase the water level. And that makes sense. As you go further and further downstream in the watershed, the tributary streams that are flowing into the river add more and more water. Pretty cool, right? Let's look at a less intuitive example. This is a graph of dissolved oxygen just north of Elkford. Dissolved oxygen is obviously important because any animal that lives in the water needs to breathe. What you may not be able to tell with this graph is any discernible trend. It looks like somebody just took a shotgun and shot it at this graph. But let's see if any of this variation can be attributed to seasonal variation. If we overlap all of the years, we can clearly see that there is a dip in dissolved oxygen around the July, August, September period. Now, why might that be? If you look at water temperature monitored at the exact same site right here, we see a mirrored graph where you have an increase in water temperature during this July, August, September period, right as when you see this July, August, September decline in dissolved oxygen. And something that we know is from experiments is that cold water holds a lot more oxygen than warm water. So something that I would like to kind of emphasize here is that visualizing data can help us to visualize trends that are perhaps not intuitive, but are naturally occurring and that are related to each other. So by monitoring different parameters, we can look at how different metrics, how they interrelate. Let's look at an infamous example. This is selenium concentrations in the Elk River at the outflow at Lake Koocanusa at the site over here. The record goes back all the way to the 1980s, and it's monitored by Environment and Climate Change Canada. And you can see a considerable increase in selenium over the years. But something that I'd like to point out here is that in this period over here, we still have a lot of variation. What could that be? If we look at the seasonal graph, we see that there's a dip in selenium levels during the May, June, July period. If that sounds familiar, it's because this is the exact period when we have freshet, when we have all of the snowmelt from the mountains coming in. And if we think about it, that actually makes sense. Here, selenium is expressed in milligrams per liter. It's a concentration. So if you take more water or more liters and add it, then the concentration of selenium goes down. So something I'd like to emphasize here is that we can look at different metrics to see how natural variation impacts parameters that we're quite concerned about. We can also look at the spatial variation of selenium in the Elk Valley. Here again, we have a graph that's ordered from the most upstream here in green, all the way to the most downstream here in blue, which is the outflow to Lake Kootenoosa. And we can see an interesting trend. We see low concentrations over here, and that kind of makes sense. It's kind of close to the headwaters. Slight increase, and then a massive increase at this yellow site over here. Well, what we know about this yellow site over here is that it's just downstream of the confluence of the Elk River and the Fording River. So all of the water that's flowing down from the mine sites around here is meeting the Elk River and increasing the selenium concentrations. Subsequently, we see a slow decline in selenium concentrations. That actually also makes sense if we think about the water flow graph, where you have an increase in water flow. And then you have a dilution of the selenium concentration as more and more water from other tributaries that are not associated with mines flow into the Elk River, thereby diluting the concentration. If we add the Fording River mine sites, Fording River monitoring stations to this graph, we see that the Elk River sites that we just looked at are dwarfed. The concentrations here are much higher. It should be noted that selenium is not the only parameter that shows this trend. This shows nitrogen, the total nitrogen concentration in the Elk River. And we see, yeah, this the same trend where you have an increase over the years. We have the same trend where you have a decrease in concentrations in the May, June, June period. And then we have the same trend where you have this sudden uptick at the yellow site, which is at the confluence of Fording and Elk River. So one of the things that the collaborative is working on right now is turning this consolidated data into a data visualization tool where you can select a parameter that you're interested in, look at all of the sites and their details that have any information in the watershed that you're looking at, select the number of samples that you'd like to look at, add any sort of tributaries that you might want to be looking at as well, and then select any of the sites that you're interested in. Click on Display Data, and it shows you the graph that I was just talking about. So we have a time series plot here, we have a seasonal variation plot just below, and then we have a spatial variation plot over here. And then you can download the data if you wish. One of the things that we have to contend with right now in the short term is incorrect data entry. A lot of the sites that we're looking at have data that's been entered in the wrong units, quite obviously. Sometimes you have blanks entered as data and incorrectly labeled. So it's going to be a long sorting process of going to the data owners and seeing if we can actually fix these issues. In the longer term, what we have to do is one of the problems is that we don't have enough data or no data at all to answer some of the important questions. One of the reasons we can actually answer some of the questions surrounding mining in the Elk Valley is because there is a ton of data. We know virtually nothing about the impacts of forestry on our water because there's not enough monitoring going on. There's a lot of things that we don't know about our water and we can't answer. But the first step would be to know what we don't know. As my boss says, know the unknowns, the unknown unknowns. So in summary, many organizations collect data on the watershed. Different ways of looking at data can tell different stories. Data can tell important stories about natural processes such as seasonal flow patterns. Data can also tell important stories about human impacts. And by understanding the limitations of existing data, we can adjust our monitoring practices to answer some important questions. Thank you very much for listening. I will take a couple questions.